Good day, everyone. This is one of the lecture videos as part of the learning materials for week 3 of EEE 113, the SEM 1 2021-2022, which is all part of the topic on electric power transmission and distribution networks. So that's my email address over there if you need to contact me. And this material is mostly based on this reference here. So this particular video is on AC power basics. So we try to produce a short lecture that can provide an introduction on AC power. AC power is a huge field and it cannot be compressed in a single short video like this. But this provides just an introduction to what's ahead. So that's me there on the right of the picture. On the middle is Dr. Mike Pedraza, our EEI director. On the left there is Sasha von Meyer, who wrote the book that we have been using quite a lot in this course. So during the EEE 113 onboarding session, someone asked for a textbook. This book is the closest that we can recommend for these 3 weeks of EEE 113 for component 1. So in previous semesters, part of these chapters were required readings, to which many students complained. So this time we're discussing this deck of slides instead. Still, students are most welcome to read these chapters. So this lecture is on from chapter 3. The electronic version is available from the engineering library. We've also made a copy in our UVLE page. So at the end of this week 3 for EEE 113, students should be able to perform voltage, current, power, and energy calculations in simple, very simple networks that model delivery of electric power. Take note that the computation of these parameters, voltage, current, power, energy, is covered in through 2 other courses, EEE 123 and EEE 133. So what we have here in EEE 113 is just a peek on what's happening and how it can be done. So as an outline, so there are 3 basic parts here. First, we introduce AC signals, which is our sinusoidal signals for AC power. And then we look at an impedance triangle and eventually a power triangle. So just 3 concepts: the signal and the important characteristics of the signal, impedance, and power. So our AC system, or alternating current system, is actually producing voltages that are sinusoidal in nature. So if you measure the voltage available at the outlet using a multimeter, you will get a voltage around 220 to 230 volts. That is the effective voltage from the outlet. However, if you have a more sophisticated measuring device, such as an oscilloscope, you will observe that the voltage is actually a periodic signal as a sinusoid shaped something like this. Yep, that's the sinusoid that you've learned in high school math. And it's commonly occurring in many things in the world, including voltage signals. So in your EEE program, this is the most common shape for voltage and currents. And hopefully this is a good introduction to the characteristics of this signal. So that signal that we have in the Philippines has a frequency of 60 cycles per second to 60 hertz. And you compare that to the DC system, this AC has a positive part, a negative part. Again, a positive part, negative part. It's a periodic signal. Every sinusoidal signal is described in terms of frequency, magnitude, and angle. So in the Philippines, the frequency of the voltage signal is 60 hertz. This means that the frequency, that the signal repeats itself 60 times per second. I trust that you can do some math and compute the period of this periodic signal, compute it in seconds. This is true for the entire power system throughout the country. In fact, all the interconnected power system throughout Luzon, is operating synchronously at 60 Hertz. In any problem solving that we will make, if not stated, then we assume 60 Hertz. We don't have to explicitly state that. The magnitude of the sinusoidal signal is likewise important. In high school math, we use the amplitude, the peak value there, to characterize the sinusoid. In this course, we will eventually use the effective value of the sinusoid as the magnitude. If you use a multimeter, just as we showed earlier, it will measure the effective value. It will show you the effective value. And we'll describe it a little bit more later. The angle or phase shift is important when we're comparing two signals. On its own, the angle is arbitrary. Even in high school math, we learned that the sine function is equivalent to a cosine function, except that they're just phase shifted. However, when two or more signals are compared, we can verify which sinusoid leads the other by some angle phi. This one, we're shown that the V here, the voltage signal, leads the current signal by an angle phi there. Since the shape, which is sinusoid, and the frequency are fixed and are implied, only two bits of information are important: the magnitude and the angle. Shown here are a voltage signal V of t, sinusoid, and a current signal I of t. Since the units are different, this one is in volts, this one is in amperes, we have an arbitrary scale here. But the phase difference here is clearly shown to be angle phi. If we are to analyze these two signals, it should be convenient to represent each sinusoid as a phasor. This voltage sinusoid here can be represented as a phasor V here, which is just a ray showing both the magnitude, the length, and the angle. So we pick the voltage as our reference and draw it along 0 degrees here. So that's the 0 degrees going to the right of your real axis. So that's angle 0 for phasor V. We likewise have current here, I of t. We represent it as another phasor, a gray phasor here, with a magnitude I, that's the effective value of the current I, and angle phi here. Take note that that angle phi there with respect to the voltage is captured here as well. That's angle phi with respect to the V as our reference. In this case, we say that the current lags the voltage by angle phi. You can imagine that these phasors are rotating in the counterclockwise direction. So this V is ahead of this current by angle phi there. Both of them are spinning at the same frequency, 60 Hertz. Let's talk about a little bit more about the effective value. We always have a sinusoidal AC voltage here. The idea is that suppose such AC voltage is applied across a resistor. So that's your VAC applied across the resistor. Because it's a resistor, we expect that heat will be dissipated through the resistor. But we ask ourselves, how much DC voltage do we apply across the same resistor such that the same amount of heat will be dissipated across the resistor? That value of VDC is said to be the effective value of that sinusoidal voltage. We know that the power dissipated across a resistor is equal to the ratio between V squared and R there. So we use that relationship. So the power is equal to the effective voltage V squared over R. But because we have a sinusoid there, the voltage is V max sine omega t, we square that, and then we divide it by R. We do some maths here. You can represent sine squared as 1 minus cosine 2 omega t here. So this now is our expression for power. We compare this to this voltage, to this expression here. Because we have a sinusoidal signal here, we simply get the average value for the power here. The average of this one here is always 0. That's a cosine function, whatever argument we have there, that will always have an average equal to 0. Therefore, the average of this expression here simply drops to v squared max over 2r. Finally, if we're comparing v effective with this expression here, then we say that v effective is equal to v max over square root of 2. So from here on, we say that the effective value of the sinusoidal signal is simply equal to the V max, that's the amplitude there, divided by square root of 2. Some of you are familiar with this. This is also the same as the root mean square of the voltage. And you can try this on your own. Do the same exercise, this time working on the currents. Suppose you have an AC current and compute for the power dissipated across the resistor for an AC current and eventually get the effective AC value for that. In terms of the phase shift, let's look at these two sinusoids again. That's the voltage signal there, and that's the current signal there. Notice that there is a phase shift here of 90 degrees. And use 90 degrees, you could be familiar with pi over 2 radians. So this time, we say that the voltage is leading the current by 90 degrees. Okay, let's ask again, which one leads the other? Let's take this slowly. The voltage is a sine function here, while the current is a negative cosine function. So some of you may have remembered from high school, the relationship between sines and cosines and negative cosines. If you can't remember, that's okay. But here's another way to look at this. The voltage hits zero crossing, positive slope here, at an angle 0 or at t is equal to 0, omega t is equal to 0. On the other hand, the current hits zero crossing here at omega t equal to 90 degrees. In terms of time, the voltage is earlier, 0 at t is equal to 0, than the current, which is 0 at 90 degrees later. Of course, we have this warning here. Because our eyes are used to reading from left to right, some of us may mistakenly think that this current leads the voltage by 90 degrees, but that's not the way to do it. Don't do that. So we look at the key state, either we look at the zero crossing here, positive slope, compare the two, which one happened earlier. Some of us would like to look at the peak values instead. The peak at 90 degrees, that's the peak at 180 degrees. This peak happened earlier, so this one leads this one by 90 degrees. So we say that voltage leads the current by 90 degrees. It is also correct to say that the current lags the voltage by 90 degrees. They mean exactly the same thing, equally correct. Let's try another one. So this figure, on the other hand, that's the current here, and that's the voltage there. Okay? You can easily see that. That's the peak value there, it's the peak value there. The current peak value happened at omega t is equal to 0. The voltage peak value happened at 90 degrees. Therefore, the current leads the voltage by 90 degrees. The voltage lags the current by 90 degrees as well, exactly the same thing. In most devices, such phase shift may not be exactly 90 degrees. In this introductory material, we confine a discussion between phase shifts between 0 to 90 degrees. So these are some of our key examples here. Voltage leads current by 90 degrees. Current leads the voltage by 90 degrees. Let me introduce to you to a transformation. So in our previous diagram, we showed a sinusoidal voltage and we showed a phasor in terms of magnitude and angle. So basically what we're saying here is if you have a time domain signal here, then we can represent this in this way. which actually looks familiar to many of us. This is a complex number with a real part and an imaginary part. This one is in polar form. This one is in rectangular form. You've done complex numbers in high school. You will recognize this easily. If you haven't done this, there's a separate lecture video as an introduction to complex numbers. So check that out. Notice that this J here used to be I in high school math. I for the imaginary component, which is equal to the square root of -1. But I in electrical engineering is a reserved variable for current, so we use J instead. So as an example here at the bottom, we can convert this time domain signal here, the sinusoid, to this phasor here. First, you convert the amplitude, that's 311 divided by square root of 2, you get 220. That's the RMS value, and that's the effective value, 220 volts. And then you grab the angle, that's 30 degrees, you copy it over there. That's your phasor there. What happens to the frequency? You can drop it. We all know that in our power system, that frequency is always 60 hertz. So that's 2 pi 60. It's an implied variable, 377. We don't need to capture that here. We can do the maths and the analysis without that information. Of course, if we're asked at the end, we all know that we did it with the frequency of 60 hertz. So this time, we extend our knowledge on Ohm's law. We know that Ohm's law relates voltages and currents. So in DC, the ratio between voltage and current is the resistance R. If you have a device here, you apply voltage V across it and current I flows through it, then we have the resistance R for this device here. In AC systems, we now have the voltage as a complex number. It's an AC sinusoid. Transform it to a phasor. That's a complex number. And then we have the current as well, represented as a complex number. If you get the ratio between these two, then we have a complex number Z here. This is the impedance Z, which can be written in its rectangular form, R plus JX. R is the real component, which is exactly the same as your resistance in your DC systems. X is called a reactance. It's a new parameter that we introduced this time. And we'll have another slide for that in a little while. So basically what we're saying here is that we now have Z as an impedance, which is now an expanded representation of the resistance that you've learned in your DC circuit. Do remember that this can be shown as an impedance triangle here. That's the impedance there, that's the resistance R there, and that's the reactance X here. Real axis, imaginary axis, and that's the triangle that's formed. So from here on, we now look at these ratios, V over I, which is equal to the impedance. Of course, if these are both DC signals, then you have R only here. This one drops to 0. If you have an AC signal, then these three components are available. So we can write this as a magnitude here and an angle phi there. That's the magnitude Z there, and is the angle phi over there. Let's look at this impedance some more. As the ratio between the voltage and the current, the impedance angle is the angle between the voltage phasor and the current phasor. I think that's an important concept to remember. The impedance angle is the angle between the voltage and the current. For simplicity in this first case here, we always use V as our reference angle. That's our V angle 0 here. Let's look at three cases. The first case here is the voltage and currents are in phase. So if V is at an angle 0, then current is at angle 0 as well. If you get the ratio between these two, V divided by I is Z, 0 minus 0 is 0. So we have a Z angle 0. Because angle 0, rectangular form, is R plus JX, but JX drops to 0. There's no reactance component. So we say that the voltage and the current are in phase. The impedance is purely resistive. Another way to look at it, if you have a resistor and you apply voltage across it, the current that will flow through it is in phase with the voltage. There's no phase difference between them. Case 2 here. Suppose the current lags the voltage by an angle phi. So it's here, our reference here, current lags the voltage, so that's I, angle negative phi here. And then we get the ratio, V over I is Z, 0 minus negative phi is a positive phi. So in rectangular form, it's an R plus JX here. The real component, and then the reactance over here. We have a positive reactance. Case 3, finally, is the case wherein the current leads the voltage. Therefore, at V angle 0, we have an I angle positive phi. So V over I is Z, 0 minus phi is negative phi. Therefore, we have an R, because that's a negative angle there, the reactance or the imaginary component is a negative value this time. Notice that this triangle here pretty much represents the first case, the second case here. This triangle here pretty much represents the third case here. For the first case, this R here, this X here is 0, this R here is exactly equal to your impedance Z over there. So these are the three cases for voltages and currents in terms of impedances, such as resistance and reactances over here. We can't cover much details for inductances and capacitance right now, but here are just simple descriptions here. Okay? Inductance is exhibited by devices when current flows through a wire. And a magnetic field, here is the magnetic field is set up around the wire. If we wind the wire to form a loop or a coil, then the magnetic field gets concentrated here. And a large inductance is exhibited by this device here. Such device exhibits inductance, is called an inductor. In a pure inductor, current lags the voltage by 90 degrees. Capacitance, on the other hand, is exhibited by devices when voltage is applied across a pair of conductors here. So you have a pair of conductor, you apply voltage across it. If you have a plate conductor that can collect significant amount of charges, then we have a strong magnetic field across it. Basically, that's a conductor there. Positive charges collect here. Negative charges collect on the other plate. And then a strong electric field will be formed between the two plates. Such a device that exhibits capacitance is called a capacitor. Across a capacitor, current leads the voltage by 90 degrees. Going back to this case here is an example of an inductive device. This case here is an example of a capacitive device. The next concept that we will cover is electric power in AC systems. We've met the triangle before, but this time it's a power triangle. We call that power is the product between the voltage and the current. With voltage a phasor, it's a complex number. Current as a phasor, also a complex number. The product between the two is another complex number. Without going through any derivation, we introduce apparent power S here as the product between voltage and the conjugate of the current. And the unit of which is volt ampere. As a complex number, we can decompose this into its rectangular form or real component and imaginary component. The real component is real power P. The imaginary component is the reactive power Q. The real power P is in watts, and it's exactly the same as the power we learned in these circuits. The reactive power Q in units of volt ampere reactive, or VAR, is associated with the power that's exchanged between inductors and capacitors. We can imagine again a right triangle here formed by these three types of power: the real power on the horizontal, the reactive power on the vertical, and the apparent power forming the hypotenuse here. Among the three, real power is still the most important type of power. Is the electric power that is converted to heat if we had the resistor, if we need the heater, or converted to mechanical energy that produces work in a motor. Strictly speaking, P, Q, and S are scalar quantities, which correspond to the length of the sides of the triangle, the P, the Q, and the S over there. Again, without any formal derivation, but you can try that. Across an impedance, the angle between the apparent power and the real power is the same impedance angle phi. So that same impedance angle phi, which is the angle between impedance Z and impedance R, works here. We say that these two triangles are similar triangles. So the real power is the power across the resistance. That real power is the power across the resistance. The reactive power is the power across the reactance. And we have some more concepts here. We say that the power factor is unity or 1 if we have a pure resistance and zero reactance. We can actually show that here, that if P is equal to S, this cosine phi is equal to 1, we have a unity power factor there, shown in the definition here at the bottom. We also define a lagging or a leading power factor. Both of them could be between 0 to 1 or less than 1 because 1 is unity power factor. If we say that the power factor is lagging, then we have an inductive device. The current lags the voltage. We have an inductive device, which is similar to this case here. The current lags the voltage, inductive lagging power factor. Likewise, we have a leading power factor here corresponding to a capacitive device where the current leads the voltage. Similar to what we had earlier, this case 3 here, current leads the voltage. We have a leading power factor for capacitive devices. So if we have a device which is combination of R and JX here, shown here as a series connected, but basically R plus JX is a total impedance there. The apparent power here is I squared R, that's real power across this resistor here, plus J I squared X, that's the power, reactive power across the reactance there. So that's a triangle as well. These are two similar triangles. That's the real power P, and that's the reactive power Q. If we have two devices in parallel, that's R plus JX. If you combine them, that's the equivalent impedance over there. But we know that the same voltage is present across both R and JX there. So we can write, again, power as I squared R here and I squared X here. Again, those two currents are not identical anymore. But we can write this current in terms of voltage times the resistance there. That current is voltage divided by the reactance, that's V over R. And so we have this expression here, V squared over R for the real component or the real power, V squared over X for the reactive power. So that's our introduction to AC power, to cover AC signals, impedance triangles, and power triangles. The next slide or the next video will have some examples for this. Thank you.